Hello guys, once again welcome back to my channel a.ß-unsaturated. I'm Faib and today I'm here with a new video on the topic chemistry. It's standard 12th NCERT chapter 12 aldehydes, ketones and carboxylic acid. This is part 3. If you haven't seen part 1 and part 2, please do watch it before watching this so you can get a continuation. So let's move on to the video. Okay, we are going to start from the example question number 12.4. An organic compound A with molecular formula C8H8O forms an orange-red precipitate with 2,4-DNP reagent and gives yellow precipitate on heating with iodine in the presence of sodium hydroxide. It neither reduces tolerance of Felding's reagent nor does it decolorize bromine water or Bayer's reagent. On drastic oxidation with chromic acid, it gives a carboxylic acid B having molecular formula C7H6O2. Identify the compounds A and B and explain the reactions involved. Solution. A forms 2,4-DNP derivative. Therefore, it is an aldehyde or a ketone. Since it does not reduce tolerance of Felding's reagent, A must be a ketone. A responds to iodoform test. Therefore, it should be a methyl ketone. The molecular formula of A indicates high degree of unsaturation, yet it does not decolorize bromine water or Bayer's reagent. This indicates the presence of unsaturation due to an aromatic ring. Compound B. Being an oxidation product of a ketone, should be a carboxylic acid. The molecular formula of B indicates that it should be benzoic acid and compound A should therefore be a monosubstituted aromatic methyl ketone. The molecular formula of A indicates that it should be phenyl methyl ketone, acetophenone. Reactions are as follows. C8H8O plus 2,4-dinitrophenylhydrazine in the presence of H2O minus gives 2,4-DNP derivative. The compound A, which is C8H8O in the presence of H2CrO4, gives the compound B, which is C7H6O2, and at the same time, in the presence of NaOH-I2, it forms the benzene ring, a single bond C double bond O, single bond ONa plus CHI3. Fourth topic, reaction due to alpha hydrogen. Acidity of alpha hydrogen of aldehydes and ketones. The aldehydes and ketones undergo a number of reactions due to the acidic nature of alpha hydrogen. The acidity of alpha hydrogen atoms of carbonyl compound is due to the strong electron withdrawing effect of carbonyl group and resonance stabilisation of conjugate base. So this is how it works. First one, Aldol condensation. Aldehydes and ketones having at least one alpha hydrogen undergoes a reaction in the presence of dilute alkali as a catalyst to form beta-hydroxyaldehydes, which is aldol, or beta-hydroxyketones, which is ketol, respectively. This is known as aldol reaction. Ethanol, in the presence of dilute NaOH, changes to 3-hydroxybutanol, which is an aldol, which is a reversible reaction, and the aldol, in the presence of heat and H2O minus, changes to but-2-NR, which is an aldol condensation product. The second one, propanol, in the presence of BaOH twice, changes to 4-hydroxy-4-methylpentane-2-on, which is a ketol. This is a reversible reaction. This ketol, in the presence of heat and H2O minus, changes to 4-methylpent-3-N 2-on, which is aldol condensation product. The name aldol is derived from the names of the two functional groups, aldehydes and alcohol, present in the products. The aldol and ketol readily lose water to give alpha-beta-unsaturated carbonyl compounds, which are aldol condensation products, and the reaction is called aldol condensation. Though ketones give ketols, compounds containing a keto and alcohol groups, the general name aldol condensation still applies to the reactions of ketones due to their similarity with aldehydes. Second one, cross-aldol condensation. When aldol condensation is carried out between two different aldehydes and or ketones, it is called aldol condensation. If both of them contain alpha hydrogen atoms, it is given as a mixture of four products. This is illustrated below by aldol reaction of a mixture of ethanol and propanol. First one, ethanol and propanol. In the presence of NaOH and heat, it changes to but2-enol, and which is from two molecules of ethanol, and 2-methyl-pent-2-enol from two molecules of propanol, similar self-aldol products, and 2-methyl-but2-enol from one molecule of ethanol and one molecule of propanol, and pent-2-enol, which is a cross-aldol product. Ketones can also be used as one component in the cross-aldol reaction. Fifth one, other reactions. First one, Cannizzaro reaction. Aldehydes which do not have an alpha hydrogen atom undergo self-oxidation and reduction. This propitiation reaction. On heating with concentrated alkali. In this reaction, one molecule of the aldehyde is reduced to alcohol, while another is oxidized to carboxylic acid salt. That is, formaldehyde plus another formaldehyde plus concentrated COOH in the presence of heat is turned to methanol and potassium formate. Second one, benzaldehyde with concentrated NaOH in the presence of heat gives benzyl alcohol plus sodium benzoate. Second one, electrophilic substitution reaction. Aromatic aldehydes and ketones undergo electrophilic substitution at the ring, in which the carbonyl group acts as a deactivating and meta-directing group. Benzaldehyde in the presence of HNO3 or H2SO4 at 273 to 283 Kelvin gives M-nitrobenzaldehyde. In chemical industry, aldehydes and ketones are used as solvents, starting materials, and reagents for the synthesis of other products. Formaldehyde is well known as formalin, 40% solution used to preserve biological specimens, and to prepare bakelite, a phenol formaldehyde resin, urea formaldehyde glues, and other polymeric products. Acetaldehyde is used primarily as a starting material in the manufacture of acetic acid, ethyl acetate, vinyl acetate, polymers, and drugs. Benzaldehyde is used in perfumery and in dye industries. Acetone and ethyl methyl ketone are common industrial solvents. Many aldehydes and ketones, example butaldehyde, vanillin, acetophenone, camphor, etc., are well known for their odors and flavors. Carboxylic acids. Carbon compounds containing a carboxyl function group, COOH, are called carboxylic acids. The carboxyl group consists of a carbonyl group attached to a hydroxyl group, hence its name carboxyl. Carboxylic acid may be aliphatic, RCOOH, or aromatic, which is COOH depending on the group, alkyl or arabe, attached to carboxylic carbon. Large number of carboxylic acids are found in nature. Some higher members of aliphatic carboxylic acid, C12 to C18, known as fatty acids, occur in natural fats as esters or glycerol. Carboxylic acids serve as starting material for several other important organic compounds such as anhydrides, esters, acid chlorides, amides, etc. 12.6 Nomenclature and structure of carboxyl group. 12.6.1 Nomenclature. Since carboxylic acids are amongst the earliest organic compounds to be isolated from nature, a large number of them are known by their common names. The common names end with the suffix "ic", acids, and have been derived from Latin or Greek names of their natural sources. For example, formic acid, HCOOH, was first obtained from red ants. Latin "formica" means ant. Acetic acid, CH3COOH, from vinegar. Latin "acetum" means vinegar. Butyric acid, CH3CH2CH2COOH, from rancid butter. Latin "butyrium" means butter. In the IUPAC system, aliphatic carboxylic acids are named by replacing the ending "e" in the name of the corresponding alkene with oic acid. In numbering the carbon chain, the carboxylic carbon is numbered 1. For naming compounds containing more than one carboxyl group, the alkyl chain is numbered and the number of carboxyl groups are indicated by adding the multiplicative prefix. Dicarboxyl acid, tricarboxylic acid, etc. to the name of parent alkyl chain. The position of COOH group are indicated by the Arabic number from the multiplicative prefix. Some of the carboxylic acids, along with their common and IUPAC name, are listed in Table 12.3. Table 12.3 Names and structure of some carboxylic acids. Structure, common name, IUPAC name. First one, HCOOH, which is formic acid, also called methanoic acid. Next one, CH3COOH, which is acetic acid, also called ethanoic acid. Next one, CH3CH2COOH, which is propionic acid, also called propanoic acid. CH3 twice CHCOOH, which is isobutyric acid, which is 2-methyl-propanoic acid. Then HOOC-COOH, which is oxalic acid, also called ethanodioic acid. Next one, HOOC CH2COOH, which is malonic acid, which is propanodioic acid. Next one, HOOC CH2 twice COOH, which is succinic acid, which is butanodioic acid. Next one, HOOC CH2 thrice COOH, which is glutaric acid, which is pentadioic acid. Next one, HOOC CH2 4 times COOH, which is adipic acid, which is hexandioic acid. Next one, HOOC CH2 CHCOOH CH2 COOH, which doesn't have a common name. It is called in IUPAC name, which is propane 1,2,3 tricarboxylic acid. A benzene ring attached to COH, which would be benzoic acid, also called benzene carboxylic acid or benzoic acid. Then another benzene ring attached to CH2 COH, which should be phenyl acetic acid, which is 2-phenyl ethanoic acid. Next one, a benzene ring on is attached with two COOH attached to it, which is phthalic acid which is benzene 1,2-dicarboxylic acid. 12.6.2 Structure of carboxylic group. In carboxylic acid, the bonds to the carboxyl carbon lie in one plane and are separated by about 120 degrees. The carboxylic carbon is less electrophilic than carbonyl carbon because of the possible resonance structure below. This is the structure they have mentioned. Okay guys, that's the end of today's video. I'm sorry if this video is too short. And if you guys like this video, please do like, share, comment. And if you haven't subscribed yet, please do subscribe and press the notification icon so that you'll be notified when I update another video. So as I said, I haven't completed this chapter yet, so I'm going to do another part, which would be part 4. So please do enjoy it too. Thank you for all your support. Bye. Take care.